确也是。我没有举啊。哦。随便你慢慢讲。你慢慢讲。没有时间了。
Extraordinary instruction. Good afternoon, ladies and gentlemen. It's my great pleasure to make this presentation today. I'm usually a master student from National Science University in Taiwan, and the title of my study is Molecular Mechanics Simulation of Adsorption Configuration of Single-Chain Deoxyribonucleic Acid aptamer upon Epithelial Cell Adhesion Molecule. And this is outline of my presentation. First, I will introduce the motivation and the background of my study. Next, the simulation method and the model of my study will show in this part. Then, I will discuss my simulation result in detail, and finally make some conclusion for my work. And cancer is one of the most threatening diseases for humans. And recently, the most challenging for cancer therapy is difficult to detect cancer cells in early stage. So until now, there are many studies pointing out that aptamer can be a powerful tool to detect the cancer target molecule in low concentration. On previous experiment study, an aptamer can recognize a specific target molecule was already found out. And the most common used aptamer is ssDNA. And in our study, we use the EpCAM as target model, and that is originally be identified as a marker for colorectal cancer. And the aptamer will choose a specific ssDNA sequence, and that is SYL3C, and it obtained from Wyson et al. In their experiment. But the adsorption structure and the activation site of SYL3C sequence binding on EpCAM are unclear and cannot be investigated in the experiment. So our study will develop the simulation method to predict the most stable structure, adsorption structure, and in order to confirm a specific adsorption and between the SYL3C and EpCAM, we also use a random sequence to compare with them. And here is our structure model. And the EpCAM we can obtain from protein data bank, and its code is 4MZV. And the random sequence, we choose identical size of sequence with SYL3C, but the base is random pick from A, T, C, and G. And here is our simulation method, procedure. And first, EpCAM and SYL3C were randomly placed in space as initial structure, it's like figure A, and approach each other by molecular dynamics, it's like figure E. Next, after the SYL3C binding EpCAM, we use the vaccine hopping to find the most stable structure of this complex, and this procedure will run 100,000 times and can obtain global minimum configuration. And finally, we take the top 3 strongest binding energy of complex to MD equilibrium in water system. And here is our simulation method. And all the molecular mechanics simulation were performed by lens package. And the force field, we use the Amber99SB. And in vaccine hopping stage, all the geometry were optimized by conjugated gradient. And in MD equilibrium, in MD stage, we use the MTD assemble, and temperature is controlled in room temperature. And pressure is 1 atm. And the TIP3P was used as water model, and the total simulation time is 10 nanoseconds. And this table is show the top 3 strongest binding energy of complex. And we can see that in water environment, the binding energy of all complex has been reduced, but the SYL3C sequence still show the stronger affinity with EpCAM than random sequence, even in a vacuum or water system. So the following analysis, we only focus on complex of SYO3C and EpCAM. And here is in a vacuum system, we perform two analyses. And the first one is counter maps. The x-axis is the show the ID of SYO3C nucleotide, and the y-axis is the residue of EpCAM. And the color bar is show the effective binding energy between each nucleotide and residue pair. And the second one is the bar chart. The x-axis is the same with the counter maps, but the y-axis is the binding energy of each nucleotide and entire EpCAM. So we see a bar chart part, and the activation site of SYO3C is in the middle fragment site and third site. And that means the entire SYO3C sequence can adsorb on EpCAM. And then we can see the bar chart of Cat3. This nucleotide has an extremely stronger affinity with residue of EpCAM, but this situation is totally different in the water system. And here is in the water system, only a few nucleotides has affinity with EpCAM, and we can see the bar chart of Cat3. The ssDNA almost lose their affinity in the water system. And then, although the different position of SYO3C sequence can adsorb on EpCAM, but as you see in the counter maps, only this position nearby residue 60 and 206 has can be adsorbed. So the adsorption structure and the activation site must be conformed in the water system, and it is necessary to equilibrium in the water system. And besides, we analyze the root mean square deviation and root mean square fluctuation of EpCAM in the water environment. And in the RMSD stage, we can see the three cases approaching stable after 8 nanoseconds. So we analyze their RMSF in time range from 8 to 10 nanoseconds. And in RMSF stage, we can see a two red circle. And the two red circles represent nearby residue 60 and 206 respectively, and they have a large fluctuation because they are interact with a number of nucleotides at the same time and leading a large fluctuation of displacement. And next, we choose a case with strongest binding energy and between the SYO3C and EpCAM, and analyze their adsorption structure. And we can see the nucleotide can into the binding pocket of residue 60 and 206. And base and phosphate of nucleotide can form hydrogen bond with amino acid. And finally, we count the number of intramolecular by hydrogen bond between the ssDNA and EpCAM. And we can see that in water environment, water will be instead of hydrogen bond of intramolecular, and all the hydrogen bond has been reduced in 10 nanoseconds. But the number of hydrogen bond of SYO3C sequence was always more than random sequence. So we can confirm the SYO3C sequence has affinity and specificity with EpCAM. So this is our conclusion of my study. And first, the adsorption structure and activation site in the water system was different from in vacuum. Thus, empty equilibrium in water environment is necessary. And next, the whole chain of ssDNA can be adsorbed with EpCAM, but the activation site of EpCAM are only in range around residue 60 and 206. And third, In the water environment, though the hydrogen bonding between EpCAM and ssDNA has been completed by water, but the SY03C sequence still shows a stronger affinity with EpCAM than random case. And next, this simulation procedure can provide a stable binding model for aptamer and cancer biomarker, and which can be further applied to other cancer study in future. And finally, we thank the National Science University and Ministry of Science and Technology of Taiwan. And this figure is show our lab members. And thank you very much for your attention.
Do we have any questions from the audience?
I know this is like a very mechanistic study between the single-strand DNA and the EpCAM binding. You also mentioned that it can be used for study cancer. Can you elaborate a little bit more on that part, like the application perspective of your study?
这是后面的，可以应用在后面的之后的，对，就是说如果我们我不用中可以，就是如果说我们有换其他的 EpCAM，然后一样可以透过这个流程，然后去看他们吸附的状况。
那研究吸附怎么样可以对你 cancer therapy、cancer study 有帮助呢？
因为我们是想说，我们未来是想走向序列设计，因为现在序列就是 aptamer 的产生都是用 ssDNA 去做，就是实验上就是去用 ssDNA 去做筛选。对，那这个过程很繁杂，那基本上都是达到11个月，10到11个月，甚至是1年多。对，就是比较长。但是如果我们通过模拟去设计序列，那我们应该可以缩短实验去